Building a Taylor series. Let's jump into it. We're going to do this nice big example where we start with Taylor polynomials and build our way to a Taylor series and talk about the radius and interval of convergence. So we want to start by finding the Taylor polynomials of order 0, 1, 2, and 3, and then the Taylor series generated by f of x equals natural log of the quantity x minus 1 at x equals 2. And then what is the radius of convergence for the Taylor series? When does the series converge to f of x equals natural log of the quantity x minus 1? So this is like asking for the interval of convergence. Let's remind ourselves for a second of the formula for finding a Taylor polynomial. So to find the nth degree Taylor polynomial, we need f of a plus f prime of a over 1 factorial times x minus a to the first, plus the second derivative at a over 2 factorial x minus a squared, with the general term being the nth derivative of f at a over n factorial x minus a to the n. Let's try to stay organized with our work here. We're going to need to take at least 3 derivatives of this function because we want up to order 3 of a Taylor polynomial. So let's go ahead and write f of x is equal to natural log of the quantity x minus 1. The first derivative is going to be 1 over x minus 1, using the chain rule, times the derivative of the inside, but that's just 1. So 1 over x minus 1. Now to take the second derivative, I'm going to rewrite this as x minus 1 all raised to the negative 1 so that I could apply the chain rule. So I'm going to have the second derivative is, I'm going to go ahead and do the derivative over here. It's negative 1, bringing that power to the front, x minus 1 to the negative 2 times the derivative of the inside, which is 1. So here's my second derivative. I'm going to go ahead and rewrite it as a quotient. So it's going to be negative 1 over the quantity x minus 1 squared. Now the third derivative of x, I'm going to go ahead and work on this one here. So I'm going to do the chain rule. I'm going to bring the negative 2 to the front. So we're going to have negative 1 times negative 2, and then the quantity x minus 1 to the negative 3. So I'm writing it like this for a reason. I mean, I know negative 1 times negative 2 is 2, but we'll see why in a second. So now I'm going to go ahead and rewrite it in a simplified way. So it's going to be 2 over the quantity x minus 1 all cubed. So we have our at least first 3 derivatives going on here, and we need to evaluate them at a, the center, which is 2. So now let's go ahead and do that. So I'm going to have f of 2, that's natural log of 2 minus 1. Natural log of 1 is 0. Now f prime of 2, that's 1 over 2 minus 1. That's just 1. F double prime of 2, that's negative 1 over 2 minus 1 squared. So that's going to give me a negative 1. And then the third derivative at 2 is going to be 2 over 2 minus 1 cubed. So that's going to be just a positive 2. So now I have all of my derivatives evaluated at a, so I can go ahead and start to substitute in my quantities to find these Taylor polynomials of order 0, 1, 2, and 3. So let's start with the 0 order Taylor polynomial. So we're going to have t sub 0 of x. Well, that's just going to be f of a. So it's just going to be this f of 2 value, which is just 0. So the 0 order, 0 degree Taylor polynomial is just 0. And then t sub 1 of x, the first order or first degree, is now going to be the first 2 terms. So we're going to have 0 plus, so f prime of 2, which was 1, over 1 factorial. So it's just 1 over 1. And then x minus a, the a value, the center is 2, so x minus 2 to the first. So we really just have there x minus 2. And then t sub 2 of x, the second order, and in this case second degree, Taylor polynomial will be the first 2 terms. So 0 plus x minus 2. And then the second derivative is negative 1. So we're going to substitute that in here. Negative 1 over 2 factorial. So negative 1 over 2 factorial. And then x minus 2 squared. And I'll just go ahead and leave it like that. And now the third order or third degree Taylor polynomial is that 0 plus x minus 2 minus 1 over 2 factorial x minus 2 squared. And then we have our third derivative at 2 is 2. So we're going to have plus 2 over 3 factorial x minus 2 cubed. All right, so we've satisfied the first part. Find the Taylor polynomials of order 0, 1, 2, and 3, and then the Taylor series generated by this function at x equals 2. So basically, we need to find a formula for the general term here. For this part, we needed a bit more space. So again, we're going to need to find this type of general term because our Taylor series is going to look like the sum of n equals 0 to infinity of the nth derivative at a over n factorial times x minus a to the n. That's our general Taylor series. Well, we know the value of a, so let's go ahead and substitute that in. So the value of a is 2. And so what we really need to do here is figure out a formula for the nth derivative at 2. And that's where we're going to come back over here and try to generalize the pattern that we see with the derivatives. So I'm going to go ahead and go a little further and take the fourth derivative here. So let's go ahead and write the fourth derivative of x is equal to, all right, so I'm going to bring this negative 3 to the front. So I have negative 1 times negative 2 times negative 3, x minus 1 to the negative 4. Let's go ahead and rewrite that here. Well, negative 1 times negative 2 times negative 3 overall is going to be a negative 6 in the numerator over the quantity x minus 1 to the 4th. Let's try to start to generalize the nth derivative at x now. Notice the pattern that whatever the derivative was, that ended up being the exponent of the quantity x minus 1 in the denominator. So the second derivative, x minus 1 squared, third derivative, x minus 1 cubed, fourth derivative, x minus 1 to the 4th. So our denominator here is going to look like x minus 1 to the n, whatever the nth derivative is. And now we have to try to figure out what the pattern is in the numerator. Well, they are alternating in sign. So notice positive, negative, and we know that the alternating factors are negative 1 to the n or negative 1 to the n plus 1. So I'm going to go ahead and start with negative 1 to the n and see if that works. So if I substitute in, let's just go ahead and check the fourth derivative here, the last one we looked at. So if we substitute in 4 in for n, then we should have a negative exponent if this is the correct one. So if I plug in 4, negative 1 to an even power is going to be positive. Oh, wait, but this is a negative. So that means it's going to have to be negative 1 raised to the n plus 1. So now if I plug in 4, 4 plus 1 is 5. I have an odd power. And so a negative 1 raised to an odd power will give me a negative. So there is my alternating factor. But what about the number itself? So we've taken into account that they alternate in sign, but what about these numbers? What's the pattern there? So for that, I'm going to have us look at these coefficients written in expanded form. So kind of just focusing here on 1 times 2 times 3. Is that ringing any type of bells? So when we multiply 1 times 2 times 3, that's 3 factorial. So again, just focusing on the numbers, not the signs. So 1 times 2 times 3 is 3 factorial. And look at the previous one. If I ignore the signs and I just focus on 1 times 2, that's 2 factorial. So the pattern is that the order of the derivative that we're taking, we do 1 less than that factorial. So in the numerator here, it's going to be n minus 1, because the degree was n, so we want 1 less than that, factorial. That's going to be my generic nth derivative at x. But I want the nth derivative at 2. So here's my general rule, but I want the nth derivative at 2. So now the nth derivative at 2 is going to be negative 1 to the n plus 1, and then n minus 1 factorial over 2 minus 1 to the n. Well, lucky for us, 2 minus 1 is 1. And 1 to the n is just 1. We needed a little bit more space. So that means -1 raised to the n plus 1 times n minus 1 factorial is the nth derivative at 2. So that's what we're going to replace right here. So our Taylor series, the sum of n equals 0 to infinity of now -1 to the n plus 1 times n minus 1 factorial over n factorial. So I just replaced that part here. I still have to be over n factorial times x minus 2 to the n. Let's do a little bit of simplifying here. So n minus 1 factorial and n factorial reduce because n factorial is n times n minus 1 factorial. So I'm rewriting n factorial as this quantity here so that n minus 1 factorials cancel. So these are gone. So here's what we're left with. The sum of n equals 0 to infinity of -1 to the n plus 1 over n x minus 2 to the n. I don't know if you noticed, but we created a bit of a problem. If I substitute in my starting value, n equals 0, I'm going to create undefined. So I actually have to change that starting index to n equals 1. And now we can do a quick check. If I substitute in 1, -1 raised to the 1 plus 1, that's -1 squared, that's 1, over 1, and then x minus 2 to the first. Well, yeah, that's the first part that comes out. And then if we substitute in 2 next, -1 to the 2 plus 1, that's -1 cubed, that's going to stay negative over 2. So 1 over 2 factorial, that's just 1 over 2. And then x minus 2 squared. And then if I plug in 3, I'm going to have -1 to the 3 plus 1, so -1 to the fourth, that's a positive, over just 3. Now here, we didn't actually reduce it down, but we can check to make sure that we actually do get 1 over 3, and we do because this is 2 over 6, which reduces to 1 over 3. So that's the proper coefficient, and then x minus 2 to the third. So this formula works. But now the question is, for what values does this function work? So what we're saying is that this Taylor series is equal to natural log of the quantity x minus 1, but only for certain values. And we want to find that set of all values where natural log of the quantity x minus 1 is equal to this power series because that's the interval of convergence. We needed a bit more space again. We need to move forward with finding the interval of convergence. We're going to go ahead and apply the ratio test. So we want to solve when does the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n become less than 1. So we're going to go ahead and substitute n plus 1 into each n here. So I'm going to do -1 to the n plus 2, x minus 2 to the n plus 1 over n plus 1. So I'm replacing each n with an n plus 1. And then the ratio test says over a sub n. This right here is a sub n. And so instead of dividing by a sub n, I'm going to multiply by the reciprocal. So anything up here in the numerator is going to be in the denominator, -1 to the n plus 1, x minus 2 to the n, and anything that was in the denominator, n, is going to flip to the numerator. So I want to know, when is this less than 1? Because the ratio test tells us that whenever the limit of the ratio, a sub n plus 1 over a sub n, is less than 1, the series converges. All right, so we can really just ignore the alternating factors because of these absolute value bars. So we have the limit as n approaches infinity of x minus 2, just x minus 2. So let's go ahead and come up here and just simplify. This is going to be x minus 2 to the n, x minus 2 to the first, and the x minus 2 to the n's cancel. Again, we're basically ignoring the alternating factors because of the absolute value bars. And we still have n over n plus 1. So we still have n over n plus 1. Okay, and then we still have these absolute value bars here. When is this less than 1? So the limit as n approaches infinity of these pieces involving n over n plus 1, that just goes to 1 because they're the same degree. We can take their coefficients. So that means that the limit evaluated becomes a 1 in here. So all that's left is the absolute value of x minus 2 is less than 1. And so once we get it in this form, once we get it into absolute value of x minus a is less than a number, that number is the radius of convergence. So the radius of convergence is 1. And to find the incomplete interval of convergence, we'll solve this inequality. -1 is less than x minus 2 is less than 1. We'll add 2 to both sides. So we're going to have 1 is less than x is less than 3. So this is incomplete because I still have to check these endpoint values here in the original power series into x. We needed more space again. All right, here was the original power series. We're going to go ahead and check what happens when I substitute in x equals 1. So we're going to have the sum of n equals 1 to infinity of -1 to the n plus 1 over n. And then if we let x equal 1, we have 1 minus 2 to the n. Well, 1 minus 2 is -1 to the n, so we're going to have -1 to the n plus 1, -1 to the n over n. All right, what's going on there? Well, let's rewrite -1 to the n plus 1 as -1 to the n, and then -1, and then -1 to the n, all over n. Well, -1 to the n and -1 to the n, there's always going to be those negatives that are going to cancel. So those two outside pieces just become +1 to the n, which is +1. So basically these cancel out, and all that's left is a -1 on the top. So I have the sum of -1, not to the n, just -1, over n. And that is basically the harmonic series. All right, so if I take the negative out, I have the harmonic series, 1 over n, which diverges. So harmonic diverges, which means that 1 is not in the interval of convergence. So my interval of convergence so far is open parentheses around 1. And then we're going to go ahead and check x equals 3 and see what happens. So we're going to have the sum of n equals 1 to infinity of -1 to the n plus 1. If I let x equal 3, I have 3 minus 2 to the n over n. Well, this time 3 minus 2 is +1 to the n, which is just 1, so we can basically ignore it. And what we have is an alternating series. We have -1 to the n plus 1 over n. And this is the alternating harmonic series, which we know is going to converge. So we know that b sub n is 1 over n. B sub n is decreasing. And we can clearly see that because 1 over n plus 1 is less than 1 over n. And the limit as n approaches infinity of 1 over n equals 0. So what we know is this series converges by the alternating series test. So if the series converges at the endpoint, it is included in the interval of convergence. So we would put a closed bracket around the number 3, and we have found the complete interval of convergence now. We needed to check the endpoints because when the ratio test gives us equals 1, which is what's happening at the endpoints, we need to check because that's inconclusive. Well, now we can definitively conclude what happens at the endpoints by checking each one individually. So to recap here, here's what I can go ahead and say from the conclusion of this problem, that natural log of the quantity x minus 1 is equal to this power series, but only for values of x between 1 and 3, not including 1, but including 3.